Hi guys! Today we discuss the dark side of fusion energy. Before we start, like and subscribe to our channel and press the notification bell so you don't miss the next video. In the Sun, bulky gravitational forces make the right requirements for fusion, but they are much harder to achieve on Earth. Fusion fuel, distinct isotopes of hydrogen, must be heated to enormous temperatures and kept stable under extreme pressure, hence compact enough and confined for long enough to enable the nuclei to fuse. The Controlled Fusion Research Program aims to achieve ignition, which happens when enough fusion reactions occur to become self-sustaining, with fresh fuel then being added to continue it. Once the ignition is started, there is a net energy yield for about 4 times as much as nuclear fission. Based on the Massachusetts Institute of Technology, MIT, the reactor's power increases with the pressure squared, so multiplying the pressure leads to a large increase in the amount of energy production. With modern technology, the most readily feasible reaction is between the nuclei of the 2 heavy isotopes of hydrogen, which are deuterium-D and tritium-T. Each DT fusion reaction releases 17.6 MeV compared with 3 to 4 MeV for DD fusion and 200 MeV for U-235 fission. Based on the mass, the DT fusion reaction releases about 4 times as much energy as the uranium fission reaction. Deuterium is available naturally in seawater, and the amount is 30 grams per cubic meter, which makes it very sufficient relative to other energy resources. Tritium is available in small quantities provided by cosmic rays and is radioactive with a 12 years half-life. Usable amounts can be made in a traditional nuclear reactor or produced in a fusion system from lithium. Lithium can be found in considerable quantities and at weaker concentrations in the seas. In the fusion reactors, the DT fusion reaction generates neutrons, and all are absorbed in a blanket containing lithium that surrounds the core. By the absorption of the neutrons, lithium is transformed into tritium and helium. For slowing down the high-energy 14 MeV neutrons, a 1-meter blanket must be used, which is thick enough. The blanket is heated by the absorption of neutrons' kinetic energy. The heat energy is removed by the coolant, helium, water, or LiPp eutectic. And in a fusion power plant, the extracted energy produces electricity by employing traditional methods. If tritium is not produced enough, some additional sources must be applied, such as using fission reactors to irradiate heavy water or lithium with neutrons. Extraneous tritium has difficulties with storage, handling, and transport. As discussed before, atomic nuclei are always positive, and to overcome 2 positive charges and repulsive force, fusion only happens at 2 high energy levels, at overly high temperatures. A fusion reaction occurs in the center of the Sun at very high temperatures, in the order of millions of degrees. Within lies the problem. It's not so straightforward to simulate the Sun. Creating such high temperatures has been extremely challenging. And since the 1930s, physicists have devised a difference of containment vessels that could bear the conditions needed for fusion. Over the 1950s, fusion had been reached, but unfortunately only inside a nuclear bomb. Scientists were assured that managing fusion for energy production will be accessible. In the 1980s, after the oil shocks of the 1970s, investment in clean, sufficient energy was high, and all eyes and interests were on renewable energies. Notwithstanding decades without any significant success, optimism predominated. All we required to solve the planet's energy problems was a jar, an electric current, and some deuterium. No one believed it, and all thought it was physically impossible, while in fact it was. The results were widely believed to be extracted from experimental error and desirous thinking. Fast forward to the present day. We are not even close to fusion compared to what we were in the 1950s. Technology has developed and changed, and now powerful lasers are ready to superheat hydrogen atoms. Notwithstanding billions of dollars worth lasers, recent progress has been incremental, and magnificent failures are still the norm. After unprofitable decades, many questions are asked if controlled fusion is even possible. Also, the enormous resources spent on fusion energy might have been better managed for more realistic energy plans, While all we know, there is no question that more reliable and cleaner energy sources are needed right now. By the way, only time will show us if fusion is the way we should choose. We can summarize the disadvantages of the fusion as below. In the sun and stars, high temperatures and powerful gravitational forces naturally prepare a fusion environment. But here on our planet, we face the challenge of making nuclear fuel hot and enough limitations to begin a self-sustaining ignition. Just think about trying to hold the plasma, a mixture of gaseous deuterium, tritium ions and atoms, and the helium fusion product, at millions of degrees Celsius. Scientists couldn't find materials that can withstand these temperatures. Therefore, scientists try to keep the plasma in a magnetic field provided by superconducting magnets around the fusion vessel/chamber. This method is tough to achieve compared to nuclear fission. So guys, that's it for today. Before the end of the video, like and subscribe to our channel. Press the bell to be notified when the new video is ready. Thanks for watching the video. Hope you enjoyed it. Have a nice day and see you soon.